And then I call this output mode C and D. And I already wrote that, that C, D is supposed to be T, IR, IRT applied to the modes A and B. In this case, the creation operator. And in fact, we just discussed before, let's assume we have an input state 1A, 1B, which is really A, B applied to the vacuum. So now I would say just try calculating the output state, or just calculate, what is in if you change the representation now from the A and B modes to the C and D modes using that matrix, what do you get? And I'll just stay up here and look what you do. Okay. Pardon me? Exactly. That'll be the result. But you've done it many times. That's good. But some people will not have done that, probably, right? So I mean, you can either view this. It's probably best to just calculate how do I get A as a function of C and D? Inverting the matrix. Very good. Which is simple in the case. And I can add that the determinant of the matrix is 1. So inverting the matrix will be very simple. In fact, it just gives you a different sign. Right, so we need A and B. So who has the output state? Yeah. No, you can't. I don't think, well, except for you can collect these two, right? These two. Right, these two. C and D will commute, yes, because they belong to orthogonal modes. I should write that down, see? Very good question. So A, B commute, and so do C and D mutually, because they belong to orthogonal modes, so they have nothing to do with each other, right? And therefore, you can collect terms that involve, so C dagger, D dagger, and D dagger, C dagger. We can just put together. So who wants to write down the state? Come on up. I'm sure your handwriting is better than mine. Very good. Sure. Yeah, I think so. All that you have to, maybe you can write just one of the, say, the A dagger as an equation in terms of. Although I guess it's clear right from here, right, that the first bracket is the A and the second bracket is B. I think that should be quite obvious. Yeah. Right. So then just. Oh yeah, the normalization. Of course, there should be a. So that's already in terms of states. Yeah, that's. Right, thank you. So that's. Right, we multiply this out, and then of course we know that A dagger applied to n gives us n plus 1 and factor of square root of n plus 1 here. And this is, this is a normalized state here of 2 photons, right? And that will also be a normalized state. In fact, if we now plug in the this usual value of the where t is equal to r is equal to 1 over square root of 2, then clearly this will go away, right? This is 1/2 minus 1/2. Then over here we have 1 over square root of 2 times 1 over square root of 2 times square root of 2. Then we had 2, 0, plus 0, 2. And there's a minus I up in front. That's really unimportant, you know, it's a global phase. How does that state look to you? Pardon me? Too many. Noon state, yes. Is it entangled? Yes, it's entangled. In fact, but this is a long debate. Now there's maybe I should put on the side. Imagine you had a single photon source outputting, say, 1 photon. I put a beam splitter here. So after this beam splitter, what do I have? I have a superposition state of either, if I call this again, maybe call this N mode D and C. So in the output, I will have 1, 0 CD plus 0, 1 CD. Is it entangled? How would you measure it? How would you measure the entanglement? Pardon me? Yes, but we have to slow down a bit. So how do you measure it? will not give you anything, right? Because it's, or another way to say it, in order to prove that there is entanglement, experimentally, I would need at least 2 different bases, right? So I can go ahead and measure in the computational basis quite easily, or I can measure in the photon number basis. So I can put a detector there and find, oh, there's no photon, or there's 1 photon. So whenever I find no photon here, there will be 1 photon there and vice versa. So what's another basis? Because in this case, I can't say, you know, it could be a product state still. Actually, it couldn't be a product state. So in fact, I agree it's entangled, but yes, what would the Bell basis be in this case? Okay, so now if we look at the possible output states, maybe 1 photon or 0 photon, then of course this would mean that we would have to measure in, say, 0 plus 1 or 0 minus 1. Okay, I'm writing them as bras, so now they are the measurement operators. All right. Except this is really a vacuum state and this is a 1 photon state. How do we make a superposition of them? How do we measure in a superposition of a vacuum and 1 photon state? Not so easy. In fact, one can measure this, of course, but whenever you look at an experiment like this, you will find that this will be part of a larger interferometer. So at some point, people will, for example, what people could do is, I don't have space here anymore, so I'll do it here. Okay, so we could imagine doing, having a local oscillator, and then we do a homodyne measurement. And we could try to measure, you know, we could try to measure in superposition basis. Basically, I mean, this is something like I guess it's something like a tiny Schrödinger cat state, if you will. And so this goes back to a point that also came up in the break. When is something entangled and when is it just a superposition? You can't say. It really depends on. You first have to define your subsystems and potentially even the measurements, but at least the subsystems. What are the subsystems? And only then can you say, is it entangled or is it just a superposition of 2 pure states? Right? So, in fact, in this, it's the same for 2 photons in a way. If for the 2 photons with 2, each has a 1 qubit degree of freedom for 2 qubits. You know, it's a 4-dimensional space, but you don't necessarily have to divide it up into the 1 qubit and the other qubit. The 4 states could also be grouped in a different way, and suddenly something that would look entangled for the 1 splitting would not be entangled in a different kind of splitting. And the fact that this can be deceiving, you know, we usually draw these pictures. Here I have my source, and here I have photons that are H or B, and there I have photons that are H or B. So out comes my state, say a psi minus, which is HV minus VH. Okay. Let's put the normalization there for once. So now this, yeah, clearly this is entangled, and also the subsystems are absolutely clear to you because there is 1 photon that's left and 1 photon that's right. Okay, but polarization modes, in a way, don't have a special property that makes them better than other choices of modes. So likewise, I could just take, if I now take a dual rail representation and I make to put two modes, one set of rails here and my other set of rails there. So now, and I still call them H and B. It's just that now that they're not polarizations, but they are different spatial modes that somehow separate. Okay? So I have that same state, but now I'm going to write it a bit different. I'm going to write it as really one, and I call this, let's say, call this HA, B, A, HB, VB. So now I'll call this 1 HA. You can't read this anymore. HA. 0 VA. 0 HB. And 1 VB. Okay, that's the first term. Minus, and then the second term. 1, 1, 0, 0. The same indices. You know, now that I have these modes here, let's just reroute them a bit. So I shuffle these indices around. And suddenly this thing will not be entangled anymore if now I make my cut in a different way. No, that won't help, sorry. I'll have to take an eraser. I think this would work, I'm not sure. Okay, so now if I make my separation between here and there, I venture it won't be entangled anymore. Maybe you can do the calculation. It's not a calculation really, it's really just a relabeling. You know, what I mean is, if, let me see. Yes, because now I have, no, that doesn't work. Well, that I hadn't prepared, that was just. Well, but it's not, no, yes, you're right, but it's not independent to what I define as subsystems. I mean, I have a superposition of something, you know, and if I in this interferometer, if I take this beam split, I complete the interferometer, I would say it's a superposition between a photon being left or right. If I give some reality to the vacuum there, which I don't have to, then in this case suddenly it's entangled between being in vacuum or being in one photon. Here. Right? In fact, if I don't know about this and this, I would say this is a dual rail qubit where the photon is either here or there. And I would say, okay, this is a superposition of a photon being here or there. And someone else would say, oh, it's an entangled state between photon being here and vacuum there, or the photon being here and vacuum there. Yes, exactly. That was the point. That likewise over there, if I'm sort of taking one mode from the right and one mode from the left, and somehow mix those, I might have to mix them first with beam splitter, and or put them into one polarization mode. Yes, that's what I have to do, I think. I put them into one polarization mode on one side, and then I would have the same thing. I would either have, then I would have, I have to think about that one. It doesn't go so fast. But I think that's an important point. If you think of a density matrix, and if it's a larger one, it becomes more complicated, right? Because if you have three qubits, you have an 8x8 density matrix. You can split that in many different ways. And in fact, for higher dimensions, people worry about this. You know, is it bipartite entangled? Is it tripartite entangled? They are different concepts. And for a larger system, it's not obvious where to make the split. If I give you a system that is one qubit, so one system with 4 basis states, you know, you can split it arbitrarily into many different subsystems and call them entangled. But it really depends on the definition of a subsystem. Well, I would say, so there's one thing, I think that's where, and that's also, I think, the only case where it's interesting for people, and that is if the subsystem partition is sort of defined by space, by real space. If you have two parts of a system, of an entire system that are far apart, then somehow relativity guarantees you that these sort of physics kind of, the situation kind of splits them for you. So you don't have to worry about redefining unless you do something crazy like here, where suddenly I take part of the Hilbert space and move it to the other side. I've done something, yeah. Well, here I've just really, so far I haven't done anything except moving them in space. But maybe next I was going to put a polarizing beam splitter between two things here, and then I would be really doing something else. Not really, because the polarizing beam splitter, all it does is makes two modes that are not parallel in space. It makes them parallel in space, but it still leaves them orthogonal in polarization. So it's really not doing anything. It's really just a router. It's like a mirror for the one. No, it's not a fantastic operation. Yes. Precisely. That was exactly my point that I made recently in Geneva when they discussed the 0-1 photon entanglement. Everything I mean, you could go even farther, right? You could say, if I prepare a photon, a particle in any spatially extended state, you could call it by the same right. You could call it entangled because it's either left or right, say, of the middle. And Nicolas Gézin would argue, yes, if you define that this is one subsystem and that's the other subsystem, then you have this kind of entanglement. But I should also add that this discussion is a bit older, and some people prefer to call this type of entanglement, where here is a vacuum state, as opposed to in photostate, we call this mode entanglement rather than particle entanglement. Okay, so that's just a. But that was a very good comment, yeah. Double slit in that sense also creates entanglement, and I don't know if Feynman would have agreed, but Yes, but here the situation is really different. We are putting two photons in, I mean, one photon each in one mode. Well, you could do this with a double slit too, right? It would actually, it might actually look interesting. So it was it's not a double slit. It's really maybe two outputs of a down converter, and you try to interfere them, which you do in the far field. Then you should also see kind of a spatial Hongo-Mandel pattern. Kind of cool. All right. So, sure. That's a very good question. I don't know what the relevance is of that, but I think there is one important lesson. That is, not even entanglement is meaningful if you haven't defined to what subsystem split you refer. And I think that's a valid point that Nicola has. It's an entanglement between modes that is potentially only filled with one particle. But you could have more. You could have, I don't know, a 1-2, a 2-1 or so. And then I don't know if it's then any more valid or less valid than with only particle back. Yes. Sure.
So, for example, why would I want to so you're looking
but it could also be a decoherence on the superposition simply, right?
Yes, that's also the notion.
Okay. That with the measurements people can usually do, you know, if you could if you, but the question is, could you actually verify it experimentally, the violation? But that. No, I agree. It's in fact they've done that, right? They in some parts. The tricky thing is that nobody has actually done it without a common phase reference, as far as I know, right? Because that's the problem. In order to measure to measure in these phases that you would need for a Bell inequality violation, just choose the standard CHSH and you choose the standard angles in this case in this 0-1 space. In order to measure that, you need sort of local energy source, right? You can't just, because it's even well, I guess theoretically you can measure a 0, but you can't measure a 0 plus 1. You don't have a detector for that. So you need a laser or coherent state. You mix it with that, and then you can get projections on these superposition bases. But the problem is if you use one laser here and another laser there, that doesn't work. They have to have a common phase. And so in effect, the argument was a long time ago that you always needed a common phase reference, but in practice that could be constructed. In principle, you could imagine having an actual local oscillator here and a local oscillator there, and then it would work. Or as Marcus says, you can also convert it, but I think you also need a phase reference, for at least practically speaking. Yeah, I think it can work without. Yeah, it can work without. So I don't know how we're doing in time, because it was actually nothing to do, but you had more questions. Okay. Pardon me? Mm-hmm. It's actually a 2 n-level systems even, right? Or infinitely. Oh, but you're talking about polarization now, or? But this is not polarization here. We were talking about vacuum versus one photon. Yeah. I mean that's the entire problem, right? Because the 0 is vacuum, it really has different energy. It's not so easy to construct measurements in the superposition basis. I just can't give you a simple passive. I can't give you a passive device that doesn't have energy itself that can put you in a superposition, because it's actually a superposition of different energy states. Mm-hmm. Yeah, but it depends a bit on interpretation. All right, long discussion. So, yeah, because what I had actually thought about doing, but it might just be too long. There's maybe one more thing we could try, and that is which is more related to this first one. It's about here. So what would happen if we actually had now a maybe a question first. What would happen if I send this state into the beam splitter? Without calculating. You can calculate too, but pardon me? The 2, 0 plus 0, 2, yes. For those who've dealt with noon states, you would know. But in fact, you can, what was the inverse matrix of that? Right here. It's exactly the same except for this global phase. Right? So what will happen if I send this as an input state? Exactly. You get the 1, 1 state back. So now, I'll write this down. It's okay. We will remember that. So then I said, the other thing I said is if we have a psi in, which will look like this. I said it was HV polarization, or let's just do this. No, let's do this one. HV plus VH in polarization, and this is sort of A, B, A, B. I said this had to come in order to have this state. How do we? All right, let's do the minus. Let's try to write this in terms of creation annihilation operators. So now we need an A dagger H and A dagger V and B dagger H and B dagger V. Just try to write that state in terms of these 4 operators operating on vacuum. Try to put that through the operation above. So put in, and now I'll give you a mode transformation. So now let's assume we have a non-polarizing beam splitter, and basically works the same for H and V. So here, H, V, H, V, H, V, and then do the exact same calculation as here. I mean, we already have the matrix here, right? We just assume that we have this matrix on the H subspace and the V subspace as a block diagonal. The matrix will be the same for both. Yeah. Okay, who wants to write down the result? Yeah, pretty much you get exactly this. So I don't know how far everyone got, but you get the same state out that you put in, right? In modes C and D. Now, okay, we don't have to write that down, which is actually very nice, which is precisely what I said earlier, that if we send in a, I would call this a psi minus state in polarization, right? And if we do this, we get the same psi minus state out of the beam splitter. In fact, I would call this an eigenstate of the beam splitter. Except that I've cheated a little bit because now this is actually two beam splitters, right? If I were to write the entire matrix here, it would be a 4x4 matrix. Like this. If this is the AH, AV, no, sorry, it's the BH, and this is the AV and the BV. So this is like, of course, it's like two beam splitters, you know, two sets of modes. And this is what a non-polarizing beam splitter does. And this is in fact the action of the Bell state analyzer. And what's nice about this would be really hard to calculate if you tried to calculate it in terms of photons. In terms of so it's easy to calculate if you plug in the creation operators, apply them to the vacuum. Because whatever you do in that case, you get a proper quantum state out. Whereas if you tried the same thing with H's and V's and tried to replace the sort of track them through the modes, it gets very tangled, if you will. And that's because it would only work if these were actually if you take this the wrong way, if you don't write down all the modes, this might become an antisymmetric state. And you can't have a boson. Can't have bosons in an antisymmetric state. The overall wave function has to be symmetric. And the creation operators will do that for you automatically. There's a paper by Greenberger about this, that very old one. So this is the action of the Bell state analyzer. Only for this polarization state and the associated wave function do we get one photon in each output mode. They will still be orthogonally polarized. And once, sort of, in one case, you will get a V and an H, and in the other case, you will get an H and a V in the outputs. But always one photon each, and that you can detect. In fact, you could even follow up the beam splitter with two polarizing beam splitters. Not so great. In which case you could detect so for a psi minus, for this one, you would get one photon detected over here and one photon detected there. For a how do I write this? For the other ones, which is the psi plus, phi plus, and phi minus, In all of these cases, 2 photons go to either side. And in the cases where, in this case, where I have HV plus VH, I still get 1 photon here, 1 photon there. The other ones, I get 2 H photons here or 2 V photons here. So they usually I can't actually detect that because my detectors, very often my detectors are so-called click detectors. They will only see 0 or something, and the something can be anything. So, but that's a technical difficulty. But even if I could detect that there were 2 H photons, I would still not know whether I could see whether I had a phi plus or a phi minus, right? Because this phase here, plus or minus, would be lost at that point. I mean, I'll detect here and I won't know the phase. So I can only see this component or that component. And there's a proof by Casamilia and Lütkenhaus. Norbert, long time ago, who proved that even if you had extra photons and stuff, you could never, I think, did he use extra photons? No, but anyway, for some conditions they proved that he could never do better than that. So you can detect sort of the psi minus, the psi plus, or that it was something else. So you can sort of get, how many bits is that? 1.5 bits instead of 2. All right. The other thing that I actually meant to do, but I don't know if we have still time, a little bit of time, that's gonna be quite a bit more complicated, because you see these, us experimentalists, we always talk about the Hongo-Mandel dip. But where is the dip here? Okay, there is no dip. There's no interference pattern. And so let's make it a bit more difficult. Quite a bit more difficult, actually. See where I start here. So we stick with the same matrix. This or that. What do we have to do to get the dip? I mean, how do we have to change the description to even be able to talk about time? So far we had modes, A, B, that were supposedly completely time and space independent, right? We didn't actually know where they lived. So what do we have to do? Think back to your normal field quantization. I had this morning, I had the electric field, and I had what do we need to describe time? Pardon me? In fact, I don't even need the Hamiltonian, because it's just, the Hamiltonian is going to be the electric field energy. So we're still talking about free modes, but I need, right. Exactly. So I need to make these time or frequency dependent, these modes. And the way I'm going to do this is by just calling them A of omega. And they will oscillate with an e to the minus I omega t. Or the, wait a second, that's the A, or the A dagger has the minus. And so I will then need that A of omega and A of A dagger of omega, I'll call it 1 and 2. delta omega 1 minus omega 2. Right, only. And so then I will write a single photon wave packet as maybe 1a, and I'll put a phi here. And that's supposed to mean d omega. Phi of omega right to the vacuum. All right, so phi is a wave packet, wave function. So this will be maybe around some omega 0, and this is phi. So this will be a wave function in frequency or time, doesn't matter. The Fourier transform of phi would then be the shape of the photon in time. So the idea is that we still stick with a single spatial mode, but now we have an infinite set of creation operators that depend on omega. Okay, and the same for B. So analogously, I would have a 1B. And in fact, for now, I would just keep the same phi. Complicated enough. And I'll call this B dagger. Right to the vacuum. And now we need one more thing. We need a time-shifted state. If we want to shift that by time, by some time tau, that's actually quite easy. That would be, well, I don't know how I call this, 1B. Or maybe I'll write so the entire input state now, call this psi tau, would then just be omega 1, omega 2, phi of omega 1, phi of omega 2, E dagger omega 1, E dagger omega 2, and then an e to the minus I omega 2 tau, which means that I shift the B by some time tau. Okay, and now we can go ahead and do the exact same replacement with operators C and D. Now we have to think about, now you calculate an output state and it's just a large integral. It doesn't really mean very much. So we actually have to define a measurement. And I guess what we want to see is the probability to detect one photon in outputs C and D. And there's various ways of calculating that. For example, I could just say that this is what I guess I call a 1C, 1D applied to our psi tau, absolute square. But I have to say what I mean here, because I call this 1 bar. It's a bit maybe not ideal. What I should really do is, of course, calculate the photo detection probability. And I don't know if you've ever looked into photo detection theory. What one should really do is calculate the expectation value of E minus E plus. Calculate the number of, get the number of photons in some mode, for example, C. And for two fields, it would really be E minus C, E minus D, T plus D, E plus C, and that would be evaluated over psi tau. Okay, that gets a bit tedious once you plug in all the mode functions and everything. It's very long. Because in the end, this only boils down to, this gives us an A dagger, no, a C dagger, a D dagger, and this gives us a C, a D and a C. And we do the normal ordering, and then we plug our input state here. It's a pure state anyway, so it's rather simple. We don't have to do an explicit trace or so. Okay. Again, what I haven't said here is it's actually the same problem with the definition there. What does the detector do? And in the simplest case, I can model the effect of the detector. The problem with that thing is still that this is sort of psi tau, but all of these would have a time dependence. So I would possibly have still 2 times T1 and T2 in there, I guess. Oh yes, EC plus, sorry. Positive and negative frequency components of the fields. And in fact, what I would, yes? C dagger, D dagger? No, sorry, this should be just the same. This is a D and a D. This is my handwriting, I think. D, D. Right, and this is also D. No? So these are the electric fields in the output modes. Yeah, that's we usually, you know, we collect the I mean the C and D commute, so it doesn't matter. I can pull them out anyways. So I could do a C dagger C and a D dagger D. But this would correspond to a sort of 2-photon detection here, right? Except that in general, these could still have different times. I could have a T1 and a T2, but what I really want is the simultaneous detection of the 2 photons. But then also my detector is never perfect, so I would actually integrate over time, over a long time. And now it's kind of nice that, so I would really have to do some kind of averaging here, 1 over T from 0 to T to do this properly. But one can do it a bit simpler by simply defining these states here. 1C I would define as a flat integral over this thing here. Okay, which is not really normalizable, but doesn't matter. And so just apply this here, and you would get something that pretty much gives you something like an output probability. Of course, that's a bit of a longer calculation with quite a few delta functions and stuff appearing. So, because you have a free evening, you're welcome to try. I don't think we can still fit it in the last 15 minutes. In the end, if you do try, it's actually, it comes out with a relatively simple expression, and then it is quite straightforward to try for phi, a Gaussian, which we never really have in the lab, but which is quite convenient. Gaussian like this, so that the integral of phi square equal to 1. So phi is the amplitude wave function, and then the integral over phi square would be equal to 1. And yeah, once you plug this all in and figure out the delta functions and take the absolute square, you can actually, in about 10 lines or so, calculate the shape of the dip. You need one more thing. You need this. What I suppose you would know how to calculate that. Does everyone know how to calculate this? Gaussian times an oscillating function? Yeah. Not really problematic. That's the only thing you will need. And then in the end, I'll give you the result. This thing PCD will look as follows. 1/2 minus 1/2 e to the minus sigma squared tau square, which is pretty much exactly what we saw in the on the slide from the Hongu-Mandel paper. Gaussian dip of a different width, of course, because now we are talking about a tau axis. And tau was the delay time between the 2 photon wave packets that we sent in. Of course, this calculation you can find in, I think, first paper was by Campos, Saleh, and Teich, early 90s, but there's find this in plenty of others, in most cases with a lot of extra formalism to cover the properties of down conversion crystals and stuff, so it makes it a lot more complicated. But from phrase, probably best to sleep over it. Thank you.